I think it's good news for this type of channel. That so is that what you're saying? That the more massive objects.
No, I'm saying that the less massive
Oh.
outnumber the more massive object by far per unit.
No, because you have to multiply the intrinsic rate, so this rate by the prior probability of both objects to be from the massive end. So if the mass distribution is, say, m to the minus 2, then draw one of the black holes from this population and the other one, and both of them have to be massive. So you lose a factor of m to the minus 4 there, right? So which cancels out. So if the distribution, the black hole mass function is steeper than m to the minus 2, then you should be dominated by the low mass objects. If it's shallower, then you should be dominated by the high mass objects.
Yeah, but dominated means if it's stepping when it's m to the minus 2, it's flat, essentially, right?
Yes, but you don't know the mass function, right? So whatever the mass function is.
The observed mass function is almost flat with the 6 events that.
But the observed mass function is this mass function convolved with this merger probability, right? Which can be, in this case, mass to the 4th power. Yeah, whatever, we can discuss.
Very short question. Yeah. Just go please to the slide where you have the supermassive. Oh, okay. I did. Okay. So,
that's solved.
About the strain determination in the case where you have a supermassive black hole and the stellar black hole in the field. So if I see correctly, it was something like you have some red line in this LIGO band. So it was not standard. Strain, the signal was not standard.
Oh, why was there oscillation in the
signal?
It's already connected. No, you mean it's fine. Here.
Okay, now we have Fabio Angelini tell us about binary merger around the massive black hole.
Okay, thank you, Ben, and thanks the organizers for inviting me. So I am a postdoctoral fellow at Sierra Northwestern University, but I will actually move in just 1 week or so to the University of Surrey in the UK with a Rutherford Fellowship from the STFC. So the work I'll talk about today is based on a paper that we recently published with Cristobal Petrovic, which is who is sitting somewhere here in the audience, and also a paper that I published last year with Fred Rasio at Northwestern University. So the question that was already raised before by Benzi is how do merging black hole binaries form, and how actually can we relate the properties of the merging binaries to the environment in which they're formed. Among these possibilities, I think, at least for me, the most exciting possibility is that many, or even most, of the binary black hole mergers that we have observed with LIGO and we're going to detect in the future with LIGO comes from nuclear clusters. They will be a very unique way to probe the population of compact objects in galactic nuclei, which otherwise it is inaccessible. Among all nuclear clusters, of course, the best case example is the nuclear cluster at the center of the Milky Way. This is really a typical nuclear cluster. It is a cluster of approximately a few times 10 to the 7 solar masses, an half mass radius of only a few parsecs, which really makes this cluster the densest stellar cluster in the galaxy. However, nuclear clusters are actually observed in most galaxies. I would say that all galaxies, approximately all galaxies of the luminosity of the Milky Way or lower luminosities host a central star cluster at their center. So nuclear clusters are really ubiquitous structures in galaxies. And they have really unique properties when compared to smaller clusters, like, for example, globular clusters. And this already tells you that the black hole binary mergers that they will produce will also have unique properties when compared to binary black hole mergers that are formed, again, for example, in globular clusters. Some of these key properties are listed here. So nuclear clusters often are observed to have young stars at their, in their center. And for the Milky Way, there is evidence that of continuous star formation throughout the age of the star cluster. And so in nuclear clusters, stars, black holes, and therefore also black hole binaries will be formed continuously throughout the age of the star cluster, while in globular clusters they're formed and also merge mostly early on during the evolution of the star cluster. So this will affect both the rates and also the properties of the merging compact objects. Some nuclear clusters, this is the case for the Milky Way, host a central massive black hole, and as Benzi said before, this really changes in fundamental ways the dynamics of stars and compact objects in the star cluster. And this will also be the topic of the second part of my talk. The third reason why nuclear clusters are fundamentally different from globular clusters is that they have much higher central concentrations, they are more massive, they have higher escape velocities. And this also, as I will show next, really has an important effect on the properties of the merging compact objects. I will discuss both nuclear clusters with and without a central massive black hole, because both are observed. The typical example of a nuclear cluster without a supermassive black hole is the cluster at the center of the nearby galaxy M33, which is also a quite typical nuclear cluster with a mass of approximately 10 to the 7 solar masses.
Is that a typical example or the only example?
It is the only well-established example of a nuclear cluster without a massive black hole, of course.
So there's a nice review by D9 that shows a nice plot with half a dozen of it, say something like that.
Well, we cannot tell for most nuclear clusters whether there is or there is not a massive black hole. But for M33, there is a very stringent upper limit on the. Yeah. How do I define the nuclear cluster? As excess with respect to the inner extrapolation of the surface brightness profile of the galaxy. Observation, anyway. Okay. So the problem is that modeling nuclear clusters with current numerical techniques, Monte Carlo models or embodied simulations, is very challenging because of the extremely large number of stars that comprise this system. So Monte Carlo and embodied simulations are really restricted to number of particles much below 10 to the 7, which is the typical number of stars of nuclear clusters. For these reasons, in this paper with Fred Rasio, we opted for a semi-analytical approach. The basic idea here is that the dynamics that determine the evolution of black holes in a star cluster is quite well understood. It's actually pretty simple. We understand it pretty well, and knowing the basic processes and the rate associated with these processes that lead to that drives the dynamics of black holes in these clusters, we can really make predictions for the merger rates and properties of the merging compact objects without running expensive Monte Carlo or embodied simulations. So we initialize simply a black hole population. We follow the rate at which the black holes sink to the center of the star cluster, the rate at which these black holes form binaries with other black holes, and the rate at which they harden as they scatter off other stars or black holes. All these rates are depend on the properties of the star cluster, and This allows us to make predictions for, again, for example, for the number of binary black hole mergers that are produced over the lifetime of a star cluster as a function of the number of stars in the star cluster. And you can see a comparison of our semi-analytical models to the Monte Carlo models of Rodriguez et al. In this plot. The agreement, I would say, is remarkably good. Our models reproduce both the scaling and the number of binary black hole mergers produced by the Monte Carlo simulations, and predict that nuclear clusters similar to the nuclear cluster in M33 should produce a few thousands binary black hole mergers over the Hubble time. We can also make simple predictions about the mass distribution of the black hole binaries. And this can be done by noticing a simple ansatz, which is that during a three-body interaction, the most massive black holes in the interaction are the most likely to form a binary. So the most massive black holes in the star cluster will be the first to sink to the center, will be the first to exchange in binaries and merge. So the average mass of the merging binaries in the cluster decreases with time, as you can see in this plot. And again, the agreement of our model to an equivalent Monte Carlo model is also in this case pretty good. We coupled these semi-analytical models to the galaxy formation models that we published 2 years ago with Enrico Barausse and Joe Silk from the IAP. And these models, these galaxy formation models, allow us to have an estimate of the number density of nuclear clusters in the local universe, which is needed to obtain a merger rate, which is found to be comparable to the merger rate per volume of globular clusters, although a little smaller by a factor of 2. But we also find that nuclear clusters produce more massive black hole binaries than globular clusters do. And therefore, the rate of mergers such as GW15 or 914 produced by nuclear clusters is slightly larger than the rate from globular clusters. And one of the main reasons for this is that nuclear clusters have much larger escape velocities, so they can retain more easily, they can keep more easily their black holes. This concept is illustrated in this figure, which shows the escape velocity from globular clusters and from nuclear clusters. Nuclear clusters have significantly larger escape velocities. These blue lines show the distribution of the gravitational wave kick imparted to black holes that are formed from black hole mergers in a Monte Carlo simulation of a massive star cluster. And this kick is due to the anisotropic emission of gravitational wave radiation, and as you can see, can reach several hundred kilometers per second and also a few thousand kilometers per second. And it is significantly larger than the typical escape velocities from globular clusters. This means that if you merge two black holes inside a globular cluster, the merger remnant would be promptly ejected from the star cluster. However, you also see that a fraction of this will be actually retained in nuclear clusters due to their larger escape velocities. So the fraction of black holes that is retained in nuclear clusters will sink back to the center of the star cluster because of dynamical friction. They will exchange again in new binaries, forming binaries with new black holes, and grow second or even third generation black holes with larger masses. You can see these new generation black holes, I think, quite nicely forming in our semi-analytical models that have higher masses and form later times than the typical black hole binaries formed in these systems. This is the total mass or chirp mass of the merging black hole binaries formed in some of our nuclear cluster models. As noted also by recently by Gerosa and Bert and Fischbach et al., the later generation black holes will have a unique distribution of their spins, because hierarchical mergers tend to skew the distribution of black hole spins toward 0.7. They will have a unique mass distribution, because they tend to be more massive than the early generation black holes, or black holes that are formed in globular clusters. And also, they have a unique distribution of redshift, because they merge at later times during the evolution of the nuclear cluster. So if a supermassive black hole is present at the center of the star cluster, this again will affect in important ways the dynamics of stars and compact objects in the nuclear cluster, and in particular all binaries that are inside a nuclear cluster with, well, most binaries that are in a nuclear cluster with a supermassive black hole will be soft, which means that the three-body interactions that in the previous slides I claim lead to the formation of black hole binaries now lead to their disruption. But even in the environment of a supermassive black hole, there are dynamical processes that can lead to a large number of black hole mergers. And one of these processes is the lead of Kozai mechanism induced by the central supermassive black hole. What we first noted is in these two papers back in 2010 and 2011 is that any binary that is inside the sphere of influence of the supermassive black hole actually forms a hierarchical triple system with the central objects. And the secular perturbation from the central black hole changes the eccentricity of the binary through the lead of Kozai process. If the eccentricity becomes very large, this can produce a merger of two stars, or even a merger of two compact objects. So in this movie here, I will show the evolution of one of these binaries. This is a binary of two black holes that orbits many times the supermassive black hole at the galactic center. The y-axis is the semi-major axis of the binary. The x-axis is 1 minus the eccentricity of the binary. So here the binary has low eccentricities, and here has high eccentricities. And so what you can see is that due to the interaction with the central black hole, the eccentricity of the binary bounces back and forth from low to high values. At the high eccentricities, gravitational wave dissipation becomes important and eventually drives the spiral of the binary that enters the LIGO band with some small eccentricity. Yeah, this is AU, and this is eccentricity. So the problem with this mechanism is that it really only works for orthogonal configurations, where the inner orbit is inclined by approximately 90 degrees with respect to the outer orbit of the binary around the supermassive black hole. This means that it only really works for a small fraction of the binaries in the nuclear cluster, using the octuple level equations of motion that describe the eccentricity evolution of the binary. What we find is that the rates are very small, and they are small by 2 orders of magnitude, smaller by 2 orders of magnitude compared to the rates that we have determined so far with LIGO detections. However, the early models assume that the binaries evolve in a spherical star cluster, but we know that nuclear clusters are actually non-spherical. This is the case for essentially all nuclear clusters in local group galaxies. They all show some finite ellipticity. So we, in this paper with Cristobal Petrovic, we looked at the effect of the non-spherical star cluster on the evolution of the binaries around the supermassive black hole. And the idea here is quite simple. So the outer orbit of the black hole binary is torqued by the triaxial or axisymmetric component of the star cluster. So if you have a binary that initially has a low inclination with respect to its outer orbit, the outer orbit of the binary is torqued the inclination between inner and outer orbit this way can change. And a binary that wasn't initially in the Lidov-Kozai regime now can acquire a nearly orthogonal orientation with respect to the outer orbit and undergo prominent Lidov-Kozai oscillations. This really now becomes a two-timescale problem. The first timescale is the Lidov-Kozai timescale, which is the timescale over which the eccentricity of the inner binary changes. And the other timescale is the precessional timescale of the outer orbit, the timescale over which the outer orbit is changing due to the triaxial or, again, non-spherical star cluster. The maximum enhancement of for the fraction of systems undergoing large eccentricity oscillation is obtained when these two timescales are equal to each other. So when the inner and outer orbit evolve over the same timescale. These curves show the cumulative distribution function of the maximum eccentricity attained by binaries around the supermassive black hole in the case of a spherical star cluster, which is equivalent to the case of no cluster at all. And you can see that when this, so these two timescales are equal to each other, the fraction of systems that reach very high eccentricities increase by almost 2 orders of magnitude. And the point of these blue and green lines is that we don't really need here to tune our initial conditions. And you get, again, an enhancement of 1 or 2 orders of magnitude, even if the outer orbit is precessing 10 times faster or 10 times slower than the inner orbit. We computed a merger rate due to this process for a Milky Way-like galaxy. We assume that stars and therefore black holes are formed continuously throughout the age of the nuclear cluster. So we assume continuous star formation over 10 gigayears. And based on the assumed IMF, we compute the rate at which black holes are formed in the nuclear cluster. This for a salpeter-like mass function or a top-heavy initial mass function. Then we use the fast stellar evolution code BSE from early 2002, but with updated prescriptions for stellar winds to compute the evolution of a population of massive binaries and the fraction of these binaries that form black holes and the fraction of these black holes, which is given here, the fraction of these black holes that are in binaries at the end of the evolution. So approximately 3% of black holes formed in our models are in a binary with another black hole. We compute the fraction of these binaries that merge, which turns out to be approximately 10 or 20% when we assume a 10% ellipticity. Multiplying these numbers together, you get merger rates, which multiplied by the number density of Milky Way-like galaxies in the local universe give you an estimate of the merger rate per volume, which is between 1 and 10 per gigaparsec cube per year. This is still small when compared to the range of values that, again, we have constrained with so far with LIGO. But it is large enough that we would actually expect to see a few or even a few tenths of detections from advanced LIGO produced by this mechanism. This is especially important because we, so as was also pointed in this paper from Nishizawa et al., the binary mergers produced through this process will have a unique eccentricity distribution when compared to binaries produced in the field or in globular clusters. So measurements of eccentricities, as also pointed out by Benzi, will help to distinguish binary black holes that are formed through this process. And this is my conclusive slide, which compares the binary black hole merger rate that we obtain in our paper with other formation channels. And that's it. Thank you.